Hi, good evening, everyone. This is week 7 for the NPTEL course Introduction to Algorithms and Analysis. This is the problem solving session, and this week's primary topics that were discussed um, were fixed universe successor, and within the fixed universe successor framework, there was a discussion on when MD was data structure. Then there was an introduction of amortized analysis and an example of one of the methods of doing amortized analysis, that is aggregate analysis. And then there was a discussion of computational geometry and how we use some of the algorithms and the analysis of the algorithms that we have learned till now in computational geometry. So what we'll do in this session is that I'll first go over some basics of the fixed universe successor, the Van Amde-Bos data structure, while taking some example problems to make them more clearer. And mostly I will focus on the problems, and the theory will just be to complement the problems and to provide more clarity. Okay, so let us start with the discussion of fixed universe successor problem. Okay, so the goal of this fixed universe successor problem is to basically maintain a dynamic subset S of size n of the universe U, right, where U goes from 0 to U minus 1. Basically, it has U entry, right, of size U, subject to the following operations. And what are the operations? So the first operation is insert, where we are trying to insert a new element X into the subset, right? So this add adds X to the subset S. Second is delete, right, where X is in S, right? So like initially the element that we were trying to insert was not in S, right? So it's in the universe, but it's not in S yet, right? So we are only adding unique elements to S. And deletion happens from the set S. Right? The third operation is to get the successor of an element X in the universe set, right? And what is the definition of this operation, right? So this is to find the next largest element, or we can say find the next element in S that is larger than any element X of the universe U, right? So it is to find the next element in basically any element Y greater than X such that Y is in S, basically, right? Where Y is in S and X is in U. So this is the successor. And the fourth operation is the predecessor operation, right? Where for any element in the universe set, we find the previous element in S that is smaller than X, right? So basically, we are trying to find Y that is less than X, where Y is in the subset and X is in the universal set, right? And again, in both these conditions, Y is closest to X for all let's say Y prime, or let's call it Y naught. Y naught is the closest to X for all Yi in S, right? So we just look for the right next element or the just previous element, right? So the first element that satisfies the condition and is in the set. Yes. So this is a um, definition of the dynamic subset that we use for a universe set, right? And the primary problem is to basically make these algorithms faster, right? So let's start by taking an example, right? So, or let us discuss one more topic before taking the example. That is the when MD was data structure. It's so primarily what we do in this when MD was data structure, right? So the first step to creating a when-MD data structure is to basically make a bit vector, right? And what does the bit vector do? Right? So the bit vector, let's call it mu, stores, right, or is defined as for all x in the universe set, the bit vector function is defined as like this, that it has a value of 1 if x is in the subset and 0 if x is not in the subset, right? So basically it's just an indicator, a bit vector that indicates whether a value is in the subset or not, right? So if you just had to take an example that let's say we have a universe of size 16 and we have 4 elements in the subset that we are defining, and the 4 elements that we are concerned with are, let's say, 1, 7, 11, 17, right? So how we define the bit vector? So this is a bit vector that we are going to use that also represents, we can say, a universe set, right? It has a size same to the universe set, 14, 50, right? So because we would need to indicate these values as bit fields in this array, so we just put 1 if the value is in the set S and 0 otherwise. And this is incorrect. Let's keep it 50, right? Because the values inside the subset S cannot be greater than u minus 1. Okay. And the next step in forming the Van der Waals data structure is to now split the universe into widgets, right? And what's the size of the widget? So basically, split the universe that has a size u into widgets of size square root of u, right? And the total number of widgets that will be formed will also be square root of u. It's a basically from widgets like this of size square root of u. Right. So in the earlier example, you would be forming four widgets because u has a size of 16 and square root of 16 is 4. No, 0, 1, 0, 0, 0, 1, 0, 1. Right. So these are the widgets that we are left with. And W3. Okay, now in the lectures you might have seen that while forming these widgets, mm, some algorithms to find the predecessor, successor for insertion and deletion inside these widgets, and by extension inside the universe set or the subset S were discussed. So I'm not going to discuss those, but from those implementations, the third step, the final step that was formed was of basically recursion, right? So recursion on the widgets, right? So basically we divide every into sub widgets of size square root of the number of widgets, right? Or you can say square root of the square root of u. And each sub widget has size again square root of the number of w, and that is right. This is primarily the main idea behind Venn and der Waals data structure, that we keep dividing these into subwidgets, first widgets, then subwidgets, then again subwidgets. And in that recursion, we make the operations that we have defined, insertion, deletion, successor, and predecessor finding. We keep making them more efficient by trying to reduce the recursive calls. This is the main idea of this data structure, right? So let's take a problem here now. What is the time complexity for finding a maximum and minimum integer in Benamde-Bose data structure? So the solution for this, or let's say first of all, the options for this is log of m factorial, b order of just m factorial, c constant lookup, constant time lookup, or the log of m, where of course m is the size of the universe, right? So, well, to find maximum or minimum, we don't need to find or check or visit every element, right? It's not a search exactly on the Venn-de-Bos data structure, right? What we can actually do is finding the minimum and maximum integer in the Venn-de-Bos data structure can be done on an associative array. So we don't need to search on the actual data structure because the minimum and maximum, the search for the minimum and maximum integer can be done on another like associative array that we make, right, for S. Therefore, the time complexity for finding a maximum or minimum integer is constant time lookup, right? Because in that associative array, for maximum and minimum, we just need to look at the first and the last element. Right? So option C. Okay, let's take another one. Right? What is the time complexity for deleting a key or integer in the Van Emdebus data structure, right? So is it m factorial, log of m factorial, constant time, or the order of log of m, right? So, well, in this case, for deleting a key or integer, we need to first of all perform a search for that key or integer inside the Van Emdebus data structure, right? And the time complexity for the search, right? Or you can even say like the deletion inside the data structure, right? So it has a basically it's for searching, right? So and in Van data structure, searching and by extension of that, the insertion and the deletion are basically performed like binary search, but on the square root of the size, right? So solving this recursion, we will get the time complexity for search and basically insertion or deletion is log of u, right? Where u is the size of the universe. So in this case, the correct answer is like the time complexity is the of the order of log of u. One more example. If S is a dynamic subset of size n of universe U, then for an element x in the universe, which operation finds the previous element in S smaller than x, right? So is it predecessor successor, insert, or none. Right, so this is of course the definition of the fixed universe successor problem, right? In which uh, we know the definition of each of the operations that we define, right? And what we are being asked in this question is that if X is an element in U, right, that finds the previous element in X, S, right? So basically, there is a Y that belongs in S, right? There is an X in U, and then you want to find Y in S such that Y is less than X, right? Because you want to find the previous element in S that is smaller than X, right? And if we say Y node for all Yi in Yi for all Yi in S except Y naught. Right, so this is what we want. Right, so if we go to the definition, right, so to get the element that is less than the value X, right, we had defined the predecessor operation, right? And the for successor, it was the next value, right? The next value that is bigger than X. So for this, like this is the definition of predecessor that is being asked here. Let us take another example. By improving the improving successor, right? That was discussed in the lectures. What is the relation of successor of x comma x in a widget? Right? It is it 2 times? Right? Is it like a sort over the widgets with equal distribution, or is it like a binary search where the size of the next widget is just like we are selecting one widget and then doing search over it and then again doing the same thing, but at every time we have a order of n operation, or is it like 3 times square root of n with a constant time operation at every time step, or is it just this? So for the improved versions of these algorithms, for the improved successor, right? The For improved successor, the time complexity was just the search over next widget and then next and then next, where each widget is basically the size of square root of the original widget that is passed, right? And this leads to a time complexity of, as we have already discussed, log of u, right? So for this, we have option D. Let's take another problem. In Venn-Debow's data structure, the size of the universe is 16. Then the universe is split into how many widgets, right? Or how many blocks. So we know that for a set U with the cardinality of U, or the number of elements in U as small u, right? We divide it into widgets of size square root of u, right? So in this case, the size of each widget is square root of 16, right? Because the size of universe is given as 16, so 4. Right, since each widget is of size 4, so the number of widgets times size of each widget is basically the size of universe, right? So n times 4 is 16, so we have 4 widgets or 4 blocks, right? We have split the universe into 4 widgets. Let's take another example. Given the dynamic set S as 1, 7, 11, 13, and the size of the universe is 16, what will the operation predecessor of 9 return? Right? Will it return 7? Will it return 11? Will it return 1? Or will it return like something else entirely? Right? So again, by the definition of the predecessor, right? For x in U, we want y in S such that y is less than x, right? And y is closest to x for all, let's say, yi in S, right? So we want the closest value to x in S that is less than x, right? So for us, x is 9, right? So which value is the first one that is less than 9, right? Or the value that is just less than 9 in S, right? So that value is 7, because 11 is basically the value that is just greater than. So if we were doing successor of 9, right, that would be 11, right? But the predecessor of 9, that is 7. So I think these problems would have helped you understand when when MDBOS data structures in a better way. And most of the problems in this week's assignment are related to when MDBOS data structure. And so I think I'll stop the meeting here.